Good morning, everybody. Sorry for the short delay. This is my first time in a lecture theatre for 3.5 years. So if you guys think you spend a long time outside of a lecture theatre, then think again. So, right, my name is Ben Rogers, and I'm going to be taking you for the second half of this fluids course. You've already been given the first half by Dr. Ravel, and so my joy is to give you the second half, okay? And you can see here that I'm going to be starting off with this nice topic of buoyancy this morning. Okay. So, before we get started, I just thought it would be useful for you to know a little bit about me, okay? So, I am fascinated by fluid mechanics, okay? I really am. Fluid mechanics is everywhere, all around us, all the time. And I spend my time here in university researching fluid mechanics and trying to develop the tools that engineers are going to be using in industry in the future, okay? So a lot of the things that I cover, this is an example here, so these are sort of coastal and offshore engineering. These are massive turbines that you can see there, and the fluid mechanics of what's going on there down the bottom, and also as the blade goes through the air, is very, very complex. Here's some work we did with one of the Formula 1 teams when we were looking at what happens to the fuel inside the fuel tank as they're going around the circuit. Then you can see here, this is nuclear waste, okay? So we hear a lot about net zero, we're hearing a lot about COP26 with the conference that's going on up there, and nuclear energy is seen as a big part of the future, but nuclear energy produces waste. So how do you deal with the waste that comes out of that particular situation? And more recently, we are, of course, looking at the flow physics due to COVID-19. So fluid mechanics is everywhere, and you can't avoid it. And we work with industry all the time, trying to understand their challenges and trying to create the engineering tools that they need. So this is an example of the kind of thing that I do. I'm hoping this plays, okay? So this is from the tsunami in 2011, and you can see, actually you can see an example of buoyancy in this video as the water comes over and it moves the vehicles around like toys, but that's enough of that very tragic event. So we can do that sort of thing very easily with what we do, with the fluid mechanics that you're going to learn during your degree here, okay? So this is just one of our simulations, and you can see that we're able to simulate these vehicles. Now, if I just go back to the beginning of this movie, test you. All right, what's that car there?
That's the teacher, that's the DeLorean.
It is, very good, well done. Your hand was up first. That was fast, okay? I've got to give it to you, that was fast. All right, very good. I just want to see if you guys have had an education before you came to us for an education, okay? All right, that's enough of Back to the Future. We are actually going to the future. So, by the end of this course, okay, you will be understanding some key concepts of fluid mechanics. All right, now, fluid mechanics, you probably realize by now, is a little bit mathematical. The maths is complicated, but what I really want you to understand are the key concepts. So we've got buoyancy, okay, and we're going to cover that today. Then at the end of this week, we're going to move on to a topic which is called the Bernoulli equation, where we start to look at the variation of pressure and velocity along streamlines. Then we're going to move on to the energy equation, understanding boundary layers and their formation, okay, in laminar and turbulent flows. Then we're actually going to go into a bit deeper into boundary layer flow, and finally we're going to finish off with some a key topic of understanding open channel flows. Okay. Now I'm going to be running a bit like Professor Rebel. Okay, I'm going to be running an online surgery hour. I've looked at your timetables, and I believe you're all free at this time. No labs, no lectures. So I will, I put the Blackboard link, the Zoom link on Blackboard already, okay, and you can just log on and ask me questions. This was very popular last year. Now, these notes are relatively new, okay? So I delivered this course for the first time last year, and when we develop lecture notes, there are inevitably little mistakes, okay? We don't do them on purpose. They just make their way in there because we're human. All right? So, if you find any mistakes, okay, I will give a free bar of Swiss chocolate to anyone finding that. Why Swiss chocolate? Well, I used to live in Switzerland, okay? So that means basically I only eat Swiss chocolate. Well, I eat other things as well, not just Swiss chocolate. All right? Now, there are gaps in your notes, okay? And where you have to fill those in the lectures, is in red, the color red, all right? So that doesn't mean it's a mistake, and it doesn't mean you can get a free bar of Swiss chocolate. This one, that's my favorite. Okay. So, the objectives of this lecture are to understand how buoyancy is produced. And it's to understand how to calculate the magnitude of that buoyancy, and to have an understanding of stability and the forces on floating objects. So what are the applications of buoyancy? So here you've got 4 examples, okay? Fairly obvious ones. You've seen these all your lives. Okay, so we've got a ship. This is actually a cruise liner. That industry's taken a battering during the pandemic. Hopefully they're coming back. Then you've got this airship, okay, so the blimp basically here. Then we have a balloon, and then of course we have a submarine. So these 2 are floating in air, and these 2 are floating in water. So there's quite a difference, in fact, between those 2. So how do we go about that? Now, perhaps more importantly, the reason why I've chosen these examples is because this is made out of a very, very thin material, but this is very heavy, okay? It's made out of metal. So why do they float? You know, why is something that's probably more dense float? Well, first of all, let's just think about what buoyancy is. Okay, so buoyancy is the upward force produced by the surrounding fluid. So the object is immersed, okay, in the fluid, and that fluid creates a buoyancy force. Now, what you can see on the left is that I have plotted here, and I've plotted there, the pressure distribution. And you'll see that because I'm going further, deeper into the fluid, the pressure increases. You've studied this already. Hopefully you studied it in high school. If not, you would have studied it with Professor Rebel. So that means that there is a difference in pressure between the top and the bottom surfaces. And this is really the key to understanding buoyancy. So let's just consider for a moment, we've got a disk, all right? This disk just here, and this disk has got a height h. And it has a cross-sectional area A, which is the same above and below. And because pressure is isotropic, okay, it's acting in all the same directions, at a depth S, below the surface here, okay, the pressure is rho gs, and so therefore the force is the pressure times the area. So rho gs times A, all right? Underneath the object, we're a bit deeper, okay? So we're a bit deeper, which means that the pressure is a bit greater. So it's rho g times s plus h, multiplied by the area. So there you can see, just by being a little bit deeper, we have a difference in pressure, and we actually have a larger pressure force pointing upwards from below. So this really helps us understand where the buoyancy force comes from. So the force on each face is the pressure times the area. The buoyancy force is the difference between the force on the top and the force on the bottom. And so if we substitute in our expressions for the forces at the bottom and at the top, and then we do a tiny bit of algebra, you can see we're left with rho F. Rho F here I'm using as the density of the fluid, okay? So it should be rho F here as well, and rho F there. So that's our buoyancy force, rho F G H times A. And we know from the right-hand side, just here, I've said the volume of my object must be the height of the object times the area. So we can now substitute in for our expression for volume, and we get rho F times G times V. Now, rho F times V, well, that's a mass, isn't it? Volume times density is a mass. And rho F is the density of the fluid. So that means that this is equal to, rho F is equal to the mass of the fluid. And in fact, that is the weight, that whole expression there is the weight of the fluid displaced. Right, so that's the buoyancy force. The buoyancy force is the weight of fluid displaced. Not the mass, but the weight. So that means we need that gravity term in there. So this is a very, very useful concept. Okay, so the buoyancy force is acting on a body immersed in the fluid is equal to the weight of the fluid displaced. Okay, so the object has displaced and has moved fluid. So that was for a nice flat disk. Okay, what about something a bit more complicated? Okay, so here we've now got a more general object, which I've drawn just here. And same as before, we have a pressure force acting, we have a pressure acting over the surface on the bottom, and then we have a pressure acting on the top. And what we're going to do is we're going to consider initially just what happens to one column of that object. Okay, so the pressure acting at the top and the bottom of that column. Now the area there should be, this should be a little h. For some reason, whenever it shows up, it always shows up as a big H. So that is delta AH. Okay, that's the area of my tiny, very, very thin column. So the force acting on that column, just like for the disk in the previous page, okay, is equal to the pressure acting on the area of each face. And in this case, the face is the top and bottom of the column. So we can say that delta FB, so delta FB here is equal to P2 times the area here, which is delta AH, minus P1 times delta AH there. Okay? So that's our force acting on the column. We then do a little bit of algebra. We say, well, delta AH is the same for both. I then factorize that out, and I get P2 minus P1. So that's the force acting on my column. Now what I'm going to do is I'm going to repeat that for lots of columns across my object. And I'm going to sum up all of their contributions. So that's what I've done here at the bottom. I've said, okay, my total buoyancy force is equal to the sum of the buoyancy force from all of these columns all the way across the object. Okay? And so we sum up P2 minus P1 over the horizontal area for all of those forces. So far so good. Now, if we make those columns smaller and smaller and smaller, you'll know from your fundamental understanding of calculus that that summation becomes an integral. Okay? So this is just basic calculus, so that summation becomes an integral. So the buoyancy force is equal to the integral of P2 minus P1, so that's the lower surface minus the top surface in terms of pressure, integrated over the area. So that's why I've got this little a at the bottom of the integral there. So that's the buoyancy force, that's the integral, and the surface A is enclosing the submerged volume. That's a very important point. Now, we know we have expressions for P1 and P2 because P1 must be equal to rho F G Z1 and P2 must be equal to rho G Z2 according to the depths of submergence. And so we just substitute that into our equation. Nice and simple. Okay, so I've just put in P1 and P2 here, and I now get the integral of rho F times G into Z2 minus Z1. But rho f and g are constant, so I take them outside of the integral. And there is my integral. Now, can anybody tell me what that integral is? Volume. Good. So this integral just here is the volume. All right? So that's the volume of the object. So we get the same expression as before. Okay, so we replace this integral by volume, and that's equal to the weight of fluid displaced. So in the 2 pages ago, I did it just for a disk, okay, but now I do it for an object in general. So I proved that this is what the buoyancy force is. This is a very, very useful concept. Okay? If you know what the weight of the fluid displaced is, you know what the buoyancy force is. So this, of course, is Archimedes' principle. Okay? So the buoyancy force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by the body. Now, the buoyancy force, very important point this, okay, it acts through the centroid of the displaced volume. So in the left-hand figure, okay, my body is completely immersed, right, by the fluid, completely immersed. So therefore, my centroid here, C, that is where my buoyancy force acts in the same way that the weight of that object acts through the centroid. But if we go to a case where actually maybe it's only partially submerged, so what happens then? All right, so now only the bottom half of that object is submerged. But the same principle still applies. The buoyancy force acts through the centroid of the displaced volume. So what you can see here is actually now my centroid of displaced volume is moved down from where it is for the weight down to some other point, because that's the centroid of the displaced volume. And that's where the buoyancy force acts, but the weight of the object still acts through the centroid of the object. All right, so there are cases when the weight and the buoyancy force act through different locations on the object. So that's just an important point for you to remember. This, of course, is the story of Archimedes, who was a very, very intelligent guy, of course. And he had his eureka moment because he was asked by the local king, when somebody gave the king a crown and said, "This is gold." And he said, "How do I know it's gold? How do I know it's not just some crummy metal that you painted gold and then you're fooling me?" So he asked Archimedes to work it out, and Archimedes realized that if he used the principle of immersion and the weight and the volumes displaced, that he could prove whether it was gold or not. Unfortunately, for the guy who gave the crown to the king, it was not pure gold. I would not have wanted to be in his shoes at that time in history. Okay, so we can do this by putting objects in fluid, which we'll go through in just a second. Now, if any of you walking around campus, the viaduct that's, where is it? It's behind us in this lecture theatre. So that viaduct is one of the longest civil engineering structures in history, but about 100 meters in that direction, you'll see that there's a sculpture of Archimedes coming out of the water in his eureka moment. All right, now I'm going to try something. So I want Piazza. Okay. Okay. So you should be able to access Piazza here. So I'm just going to ask you a question. So let me go back. All right. So here's a short problem. Okay. We've just worked out that the buoyancy force on an object is equal to the weight of the fluid displaced. So here's problem number one for you guys to work out. So if you're not on Piazza, please go on it right now. So here we've got a 3 kilogram copper cube and a 3 kilogram copper ball immersed in a liquid. Here's the question. Will the buoyancy forces acting on these bodies be the same or different. All right, so let's now go to piazza. Can you guys see the piazza pole, by the way? No, let me... Oop. I think I need to publish it. Right, now you should be able to do it. Okay, so your options, are they the same or different? So if I scroll down, I should be able to see who's viewing. Oh. All right. Okay, so we're doing the count. We've got about 40, got about 50 people, and there's a lot more than 50 people in here. So, 85% of you think the same, but an increasingly large proportion think it's different between these two. That's interesting. I'll just give people a few more seconds. All right. Okay, the answer is it's the same. Why? Why is it the same? Let's think about it. Right? You have a copper cube and a copper sphere. They both have the same mass. They both have the same density because they're both copper, right? So what's the volume? The same. By definition, the volume must be the same. So the volume of displaced fluid is the same. So the buoyancy force is the same. But let's go to the next one. Right. Now we've got two 5-centimeter spheres or balls, okay? One is made of aluminium, and the other one is iron. Both of them are submerged in water. Will the buoyancy forces acting upon these bodies be the same or different? So let me go to the other piazza pole. All right, the poll is open. Are they the same? Are they different? One's made of aluminium, one's made of iron. Okay, we have about 75 votes in, going up, 80. See if we can get to 100. All right, we're up to 95 votes. I think I will put you out of your misery. Very interesting here, very interesting, okay? So before, all of you were absolutely certain. Yeah, it's the same, okay, hey. Now you're not so certain. In fact, it's actually, it's a bit closer. So what is the answer? Well, they are the same. Why? Why are they the same? Okay, you put your hand up, yes? You're very quick putting that hand up. Yeah, it's like...
Sir, they are the same because in spite of the fact that they have different densities, they are the exact same shape and they are the exact same volume. The exact same volume displays the exact same volume of water. Therefore, the exact same amount.
Thank you very much. Very well done. everything was correct just for one point he mentioned when he said that they're the same shape. It doesn't matter what the shape is, it's the volume. Okay, it's the volume of fluid displaced. But very well done. And that takes a bit of courage to do that in a lecture theatre full of hundreds of people, I can tell you. All right? So, I can't really say it any better than he did, to be honest. So the buoyancy force is the weight of fluid displaced. It's the same because they're the same size. All right, let's move on. So I think we're getting a good idea now about buoyancy force, but some of you need to go back and think again a little bit about it. That's what that all is very useful for. So now we've got different floating bodies, okay, but whether something sinks or it rises depends upon the ratio of that density to the surrounding fluid, okay? So the buoyancy force at equilibrium is going to be equal to the weight, okay, of the submerged object. So if we substitute expressions in for the buoyancy force and we substitute expressions in for the object, so the object here, I said that the weight is equal to the average density times gravity times the volume of that object. And you can see that the gravities cancel, and we can then get this nice equation here of the submerged volume over the total volume. And that's equal to the ratio of the average density over the density of the surrounding fluid. Okay, so this means that our body is perfectly suspended. But if we have what we call positive buoyancy, okay, then in fact the average density of the object is less than water, and so our object will rise to the surface. Conversely, okay, when we've done neutral buoyancy, when we have an object that is more dense than fluid, then it sinks. And hopefully you would have studied this at some point in school, if not in the kitchen sink in some way at home. Okay? Now, that's very basic, but let's move on to something a bit more useful in terms of engineering, which is this idea of specific gravity. And you'll often hear engineers in industry say, tell me what the specific gravity is of the object or of the fluid. Okay, tell me. So what is specific gravity? Well, that's the ratio of, it's the ratio of the density of the object over the reference density. Now, we're on planet Earth, so basically our reference density is the density of water, but it doesn't have to be, okay, so keep that in mind. Now, if we multiply the top and bottom of that equation by g and the volume, okay, then we get that the specific gravity is rho times g over rho f times g times v. Well, this is quite simply the ratio of the weight over the buoyancy force. So this is what specific gravity actually really is. This means that we can work out what the specific gravity of an object is by measuring its weight outside of the fluid and inside of the fluid, okay? Because we know what that is. And then to work out the buoyancy force, we just replace that by the weight minus the apparent immersed weight when we put the object in the water. Okay, so that's specific gravity, very useful, but that's for a solid object. Easy, all right? But how would you do that for a fluid? You can't just stick the fluid in your reference fluid because then it all goes everywhere and you can't measure anything. So this is why you have hydrometers, okay? And hydrometers are used to do that. So what we do is we have a tube here and we put our liquid that we want to measure the specific gravity of down in the bottom, and this thing is set up so that the depth that the tube submerges when we put the fluid in gives us this value delta z, and then from delta z we can work out what the specific gravity is of our object. So this is how engineers do it in reality. Now, this is a very simplified version. If you go to industry, you'll find they use something much more complex than that, but the concept is the same. So let's get on to something a bit more interesting. Okay, submarines. How do they change submergence? So what you have in the submarine, of course, is that you have these ballast tanks, both in the middle of the submarine and at the forward and the front of the submarine. And it uses this concept of displaced weight of water in order to go up and down. Sounds simple. So in order to submerge, okay, they let water in, okay, this reduces the volume of water that's displaced, and because that volume is displaced, their buoyancy force decreases, and so the submarine can go down. Similarly, when they want to go up to the surface, okay, they have compressed air, and so they force compressed air into these ballast tanks just here, okay, which expands, and it expels the water, so the water goes out of the submarine. This increases the volume of fluid displaced, and that increases the buoyancy force, and so the submarine goes up. And you've got one at the front and one at the back, which is doing the same thing, because it creates a force just there. So a very clever idea. But this is just a classic example of how we use the concept of buoyancy and how to change the buoyancy by changing that volume of displaced air. Now, you've also got the issue of stability. Life isn't all simple with buoyancy. So any of you who've been in a boat will have felt the rocking and an occasional slight wary moment. You think, oh, are we stable? And an object is inherently stable when it returns back to its sort of equilibrium position. The trouble with boats is that you can get a moment which is not in equilibrium, or it's not covered by gravity. And so we have something called rotational stability. A very important concept for naval architects is this idea of a meta-center. Okay? So the meta-center is the intersection point of the lines of action of buoyancy and the line of symmetry. So in the left-hand case, you can see this is a perfectly horizontal boat, okay? And the buoyancy force goes through that line of symmetry. But when the boat goes over just to one side, okay, now the buoyancy force is actually still pointing upwards, but our line of symmetry is at an angle, and so we have this metacentric point just here. And the position of that metacentric point dictates whether it is stable or not. So a floating object can be stable when the metacenter is above the center of gravity. So if this metacenter is below this point, then it is unstable. That gets quite complex. That's the furthest that we go with that at this point in the course. Now, what about compressibility? We just saw the case of a submarine, okay, where you're pushing compressed air in, but then you're letting water in. How does compressibility affect the stability of a craft? So, as I state just here, it is inherently stable if the object's compressibility is less than that of the surrounding fluid. Okay? The body will remain in an equilibrium state. The physics of this gets a bit more complicated, but this is why this is stable. Okay? So when you're in a hot air balloon, you are stable because the air inside here is hotter, okay? It's more compressible. Sorry, it's less compressible, and so it is stable. But it's the opposite for the submarine in the bottom picture. Those are concepts that you'll come back to later in your course. Okay, I'm just highlighting to you at this point in the course what you should start to think about. So let's do a worked example. And let's try and work out how we use this new idea of the weight of displaced fluid, okay? So the question says, a hot air balloon must be designed to support a total weight of 1,300 newtons. The ambient air is at 20 degrees Celsius, and the hot air inside the balloon is at 70 degrees Celsius and 100 kilopascals. Both of them are at 100 kilopascals. The question says, calculate the diameter d of the spherical balloon that will just support the total weight. So that means it's at equilibrium, right? So it's just supporting the total weight. We give you a little hint, okay, assume that the volume of air displaced by the weight down here is much smaller than the volume of the balloon, okay, which is how it would be in reality. Obviously, you've got some useful information. In case you've forgotten, the volume of the sphere is 4/3 pi r cubed, and r here is the diameter over 2. And we have gases, so we have to have an equation of state. So that's pressure is equal to rho times RT, and those are we have our gas constant just there. All right, so how do we go about answering this question? We have to ask ourselves a question in order to answer the question. The first question is, what are the forces acting on the balloon? Well, obviously, we have three forces acting. We've got the weight, W1. We're going to call this W1 for our analysis. That's 1,300 newtons. We've got the weight of the gas inside the balloon. We're going to call that W2. And then we have the buoyancy force, FB, all right? So those are our forces. These forces are all acting vertically, and that's our free body diagram with the forces acting. The balloon is not moving, and it is therefore in equilibrium, so the upward forces must balance the downward forces. There's no shocker there, all right? But the equation must be that the buoyancy force, FB, must be equal to the combination of W1, so the weight, plus the weight of the gas inside the balloon. All right, so that's the first thing. Okay, we've understood what forces are acting now, but how do we formulate those forces? How do we get FB and how do we get W2? We know what W1 is. We've been given it. So the buoyancy force must balance, okay, the weight of the object and the weight of the gas inside the balloon. The supported weight is 1,300 newtons, nice and easy. The weight of the gas in the balloon must be equal to the density times gravity times volume. Okay, so nice and simple equation. So we've got the density of gas, rho g, we've got gravity, and then we've got 4/3 pi d upon 2 all cubed. Okay, so we've got an expression for D. That's what we're after, capital D. The buoyancy force is, of course, very similar, except that this is the weight of fluid displaced by the balloon. The weight of fluid displaced is obviously the density of the air times gravity times the volume. So we're getting there. We're able to answer this question now. We have expressions for the buoyancy force, we have expressions for W1, and we have expressions for W2. And we can substitute all of those expressions now into our top equilibrium expression. So let's go ahead and do that. So that's what we have here on this screen. So FB is equal to W1 plus W2. So here's my buoyancy force, FB. Here's W1, which we're given, and then here's W2. Now we just do a little bit of algebra, and we rearrange that equation to solve for the diameter d. That's what the question asks for. So we end up with this expression that d upon 2 all to the power 3 is equal to 3W1 over 4 pi g into rho of air minus rho of gas. So these are the only two things that we don't know now. And if we know what those are, then we've solved our problem. So now it's just a question of using the equation of state. Now, some of you might know that as the ideal gas equation. You can use it in this context because the gases are behaving in an ideal way, but generally it's better to refer to it as an equation of state. Okay, so this is how we find the gas densities. So there's our equation of state at the top. P upon rho is equal to RT. So density of air is equal to P, the pressure of air over R times the temperature of air. If you remember, we were told the air was at 20 degrees Celsius and that the pressure was 100 kilopascals. So we get an answer of 1.19. We do the same for the gas, and we get a density of 1.02. We can now substitute those values into our expression there, and we end up with an answer That's a d upon 2, all to the power 3 is 186 meters cubed. But it ends up that the diameter is 11.42 meters. Okay? So it wasn't that difficult a problem once you broke it down. What are the forces acting? Okay, how do we formulate an expression for the forces given our knowledge of buoyancy? So, in this lecture, we have covered some key concepts. Okay? First of all, we discovered that buoyancy arises from the difference in the pressures acting on the upper and the lower surfaces of the object. The buoyancy force is equal to the weight of the fluid displaced. We talked a bit about the Archimedes principle and specific gravity. And at this point, I have one final question for you, and I will give you the answer in the next lecture, so don't you need to put your hand up. All right. Let's think about that balloon that we have submerged in the water, okay? The balloon is at equilibrium. That means that we've got all of our buoyancy forces and our weight all in the right order. But then, what happens, okay, if I pull the balloon down just a tiny amount? If I just put it down just a tiny amount, what happens? Okay? That is your question to think about for 3 days. At this point, I'd like to thank everybody in the audience for wearing masks. We do appreciate it. And I will see you on Thursday. Thank you.